There is plenty of oxygen on the moon. Metals, silicon, solar energy, even water at the poles. On paper, it looks almost sufficient. And yet, if you try to design a permanent self-growing settlement, one that mines, manufactures, grows food, and expands, you run into a quieter constraint. Not radiation, not temperature, not even energy. A handful of elements determine whether the system closes. Today we will apply the Settler's Guide framework: hostility, energy, volatiles, materials, and access, to ask the harder question: does the moon actually contain what a self-growing city requires? Some of you followed the Settler's Guide to Mercury. Most people assume Mercury being the worst possible place in the solar system. It turned out, however, to be surprisingly competitive. Now we will look at the moon. Most people assume that the moon is the second easiest option. Mars looks more Earth-like. That assumption deserves examination. Not whether we can visit, not whether we can build a research outpost, but we want to look at whether the moon contains what is required for permanent self-growing settlement. The Settler's Guide framework evaluates any world through 5 lenses, not specifically lunar lenses, but generic settlement lenses. 1. How hostile is the environment? 2. How easy is it to produce energy? 3. Are all key volatiles, water, nitrogen, carbon, etc., available? 4. Is there a sufficient suite of structural and industrial materials available? And 5. How hard is it to get there and to stay connected with Earth? We will apply these same 5 questions to all worlds in the solar system in this series. It will take a while, there are many places to go. The answers for the moon are not what most people expect. Hostility. The surface of the moon is deadly at settlement timescales. No atmosphere, hard vacuum. The temperature at the equator swings between plus 130 degrees Celsius at noon to minus 180 degrees before dawn. At atmospheric pressure, that would be from hotter than boiling water to just 5 degrees warmer than oxygen-forming puddles on the floor. And the night lasts 2 weeks. The ground is covered with regolith, mainly consisting of extremely fine, razor-sharp, electrostatically charged dust that destroys seals, clogs filters, and gets into your lungs. And radiation, between 380 and 500 millisieverts per year at the surface. The higher end when the sun's magnetic field is the least protective. For comparison, this is 200 times of normal Earth background radiation. The thing is, none of this is actually surprising, and none of it is the hard problem. The hard problem is the regolith itself, typically 4 to 5 meters deep in the Mara regions, up to 15 meters in the highlands, and that's before you reach not quite bedrock, but somewhat solid, albeit fractured bedrock called megaregolith. But all the issues resolve if you can get underground. Getting underground means getting into rock, or putting a lot of regolith on top of you, moving a lot of regolith to get there in the first place. And regolith does not consolidate. It wants to fall back into any hole you dig, and it brings that fine abrasive dust with it. Piling more of it on top of a surface habitat doesn't help that much either. It takes meters and meters. 1 meter will only reduce chronic radiation dose by about 25%, still way above safe levels. You need solid material overhead, and you need a working environment where your equipment is not being destroyed by abrasive particles getting into everything. So, bedrock. Digging down through 5 to 15 meters of regolith is one option, slow and unpleasant, but doable. The smarter approach would be to start where bedrock is already exposed. Crater walls and rills do that in places. And in some regions, the Moon offers something even better: lava tubes. Volcanic tunnels left from the Moon's early geological history. Some of them hundreds of meters wide, with solid basalt ceilings tens of meters overhead. Inside one of those, radiation drops to below Earth background, less than 1 millisievert per year. Whether you find a lava tube, tunnel into a crater wall, or dig down and line your shaft, the principle is the same: meters of rock overhead. Rock dust works, but it takes more of it. The Moon rewards the builder who goes deep. One separate hazard worth flagging is the solar particle events, sudden bursts from the Sun, sometimes strong enough to be lethal on the unshielded surface. Unlike galactic cosmic rays, these are stopped, though, by just a few centimeters of anything solid. And unlike cosmic rays, they come with a warning. Solar monitoring gives you minutes to hours of lead time. And we already do that. The rule for surface work is simple. Always keep your suit radio tuned to the solar weather channel, and always stay within reach of shelter. You don't need a deep shelter, just a roof. Your rover has one. The bottom line on Hostility: the Moon's surface is lethal. Underground, though, survival is an engineering problem. Those are two very different things. And the more interesting engineering constraints appear elsewhere. And energy. The Moon gets about 30% more solar energy per square meter than Earth's surface. No atmosphere, no weather losses. The problem is not intensity, the problem is time. The day-night cycle. 2 weeks of sunlight, 2 weeks of darkness. Storing energy for a 354-hour night is not a trivial engineering problem. It is probably the largest single infrastructure challenge for a non-polar base. But it is not unsolvable. It is engineering and operational question. The physics of thermal storage is proven. Ground source heat pumps have been in residential and commercial use for decades. On the Moon, you have abundant rock to store heat in, and a vacuum that is an excellent insulator once you seal your structure. A settlement can shift its load into monthly cycles: heavy smelting and tunneling during the 2-week day, education, maintenance, manual work, and other things that doesn't require as much energy during the night. Green plants even tolerate variations. A regular 14-day cycle of warm and bright followed by cool and dim for 14 days will considered weather by the plant, not a catastrophe or disaster. If the difference is matched, you can't have too bad weather for the crop. At the poles, the situation is more favorable still. Crater rims near the pole receive near continuous illumination, what the literature calls peaks of eternal light. Some sites at the lunar South Pole receive sunlight over 90% of the year, but the area of these high illumination ridges is extremely limited. A few hundred meters across, measured in fractions of a square kilometer total for the best sites. It is enough for a research outpost, but certainly not enough to power a city. One possibility for a growing lunar city would be to add solar farms along different longitudes connected by power cables. The constraint is incidence angle. The sun is essentially at the horizon, so panels must be vertical. And careful siting is needed to avoid one farm shadowing another. Nuclear is also on the table. The Moon has uranium and thorium concentrated in KREEP-enriched geological regions. We'll come back to those. And helium-3 is everywhere, although fusion power is still 20 years from being realized. For an early settlement, solar is still the obvious starting point. Volatiles. That is where it gets difficult. Oxygen is not a problem. The Moon regolith is about 45% oxygen by mass, locked up in silicate minerals and metal oxides, but extractable with heat and the right chemistry, or just putting electricity through it. Oxygen for breathing and for rocket fuel is probably the Moon's most easy resource challenge. Water is more complicated. We know there's water ice in permanently shadowed craters at the poles, craters that haven't seen sunlight in billions of years, cold enough to trap volatile ices for eons. The L-Cross mission in 2009 deliberately crashed an impactor into one of these craters and measured the debris cloud. The result was 5.6% water by mass in that specific location. Estimates for south polar ice range from hundreds of millions to several billion tons. That's a genuinely useful amount of water. But here's the problem that almost never gets discussed: nitrogen. Agriculture uses nitrogen. Plants uses nitrogen. All of it. Protein synthesis, atmospheric buffer, fertilizer. The Moon has almost no nitrogen accessible outside the polar permanently shadowed regions. And even there, the nitrogen source is ammonia ice at trace concentrations, 0.14% in the L-Cross plume. It may be present at higher concentrations below the surface, in other PSR locations, and at large carbonaceous meteorite impact size, which could be outside the poles area. But we have no hard data supposing either of that. The dry regolith does have some solar wind implanted hydrogen, nitrogen, but only at levels of tens to hundreds of parts per million. That is not recoverable at settlement scale with any process we currently know. Carbon is similar, trace in the dry regolith, more in the polar cold traps, but still poorly quantified. Thus, there will be more than enough oxygen. Water, and therefore hydrogen, is available if you go to the poles. Nitrogen and carbon are the really difficult elements. A settlement that aims for genuine agricultural self-sufficiency need to either be at the poles, processing large volume of permanently shadowed regolith, find a carbonaceous meteorite with some elements still available, not evaporated on impact, so at a low impact one. There is said to be 5 of those within the last 3 gigayears. Or the colony or settlement could import and carefully cycle its nitrogen and carbon, and if it reached near zero losses, the import will be minor, and it could, as long as it can export something else or have enough stored, it would be fine. Neither of these are impossible. Nitrogen is the constant that most casual settlement discussions underestimate, though. Materials. Structurally, the Moon is reasonably well stocked. Aluminium, iron, titanium, magnesium, calcium, silicon, all available in the regolith in meaningful concentrations. Silicon means you can make solar panels locally, which is significant. Metals means you can make metals, which is even more significant. There is no copper to speak of. There is no wood, obviously, and carbon is scarce. Phosphorus and potassium, the P and K in APK fertilizer, are globally scarce. Here's where the Moon has a genuinely interesting geological feature. The Procellarum KREEP Terrane, a large province covering roughly 10% of the lunar surface on the near side, is enriched in potassium, phosphorus, rare earth elements, uranium and thorium. This is a direct consequence of the Moon's formation. When the lunar magma ocean cooled, incompatible elements concentrated into a large residual melt that pooled in this region. For a settlement, KREEP is where you get your fertilizer feedstock, your rare earths for electronics, and potentially your nuclear fuel. The problem is that the highest KREEP concentrations are in the equatorial and mid-latitude near side, centered around Oceanus Procellarum and Mare Imbrium. The best water ice is at the South Pole. A fully self-sufficient settlement, one that doesn't depend on sustained Earth resupply, probably needs access to both. That means either a northern site with access to fringe creep and any cold traps it can find, or a long-range surface transport between the polar base and the creep mining operations. Or most likely an early period of importing the low-volume, high-value deficits, which vary depending on where you are. Primarily nitrogen and phosphorus. Sulfur is worth a brief mention, not because it's rare, but because it is a fair bit of it. At about 700 parts per million in the regolith, it is present in concentrations useful enough that sulfur concrete, using sulfur as a binder instead of Portland cement, has been seriously proposed for early lunar construction. No water required in the mixing process. That matters. Travel and access. This is the Moon's main advantage over every other settlement candidate, except Earth orbit, and it's pretty close to that as well. Travel time to the Moon, 3 days. Radio signals, 1.3 seconds, communication lag. Rescue, if something goes wrong, you need to wait perhaps a week for rescue to arrive to take you home to Earth. Or take you to safety of Earth. It might not be your home. Launch windows are daily. Compare that to Mars. Travel time 6 to 9 months. Radio lag 3 to 22 minutes. You're not waiting that much if you're sitting talking to someone. Rescue, if you can wait, 6 months to 35 months if you're on the wrong side of the sun. The launch window is every 26 months, so you have to wait over 2 years for the next opportunity. The Moon is, in effect, operationally close. That statement sounds obvious, but its implications are profound. It means that the Moon is the only place beyond Earth where you can run a genuine industrial test program. Try something from in situ resources. Fail, fix it, try again. It means rescue is possible. It means that it is reasonably practicable to resupply from Earth while you figure out how to complete the local industry or how to tweak your recycling of things that are difficult to find on the Moon. That access to the industrial support from Earth is an enormous advantage in the early phases of settlement. So, let's run the score. The Moon is genuinely hostile at the surface, but perfectly manageable underground. It has abundant solar energy anywhere. At the poles, it is continuous. Everywhere else, it is a tricky storage problem, 14 days, but it is a solvable one. There is water and carbon, probably, at the poles, and a nitrogen constraint that will take careful deliberation. Most of the structural materials a settlement needs are available at reasonable quantities, with carbon, phosphorus and copper as the notable gaps. Mostly solvable, we believe. And the Moon is just 3 days away from Earth, practically a stone's throw. The Moon does not fail on resources, except possibly nitrogen and carbon. It will fail if the settlement cannot integrate what is available into a working system. And that, the integration problem, is something that we, you and I, anybody, can start working on right now. You do not need to go to the Moon to figure out whether you can grow your favorite food within a Moon-relevant energy cycle. High light and temperature for 14 days, dimmer and cooler for 14 days, and keep cycling that. How much dimmer and cooler is the trick question here. Making it dark will probably kill plants. You can also check whether an electrical motor with aluminium wire instead of copper wire has comparable performance. You can check whether a wall built from sulfur concrete without water has adequate strength and pressure containment. That is precisely what analog research facilities are for. The moon will not fail because it is harsh. Underground, hostility becomes engineering. It will not fail because it lacks oxygen. It may fail because certain elements are scarce, and scarcity forces dependence. A self-growing settlement is not defined by survival. It is defined by whether its critical loops can be closed locally. On the moon, oxygen is abundant, nitrogen and carbon may not be. And that difference will determine whether the moon becomes a permanently supplied outpost or the first settlement beyond Earth, stable and growing.